And welcome everyone. This is Joe Armstrong in the December Power Systems Virtual User Group webinar. Merry Christmas. God, Christmas is like right around the corner here. It's pretty exciting, one of my favorite times of the year. Before we get started today, I do have one announcement, and that is about the Apache Log4j vulnerability. So I was asked that maybe I put out there a link to the PCERT. So IBM is all over this. We've got some links out there that show you which products are not affected, and we're busy taking care and updating our products that might be affected. So if you want some information on this, I'll put in the chat session as soon as I get done with all this introduction stuff here. I'll put in the chat session a link to the PCERT out there that has all these other links about what you can go to and look at and see what IBM's doing on this. So wait for that, okay? So next in is I am recording this, so the recording is on now. I don't know why anybody would have a problem because nobody's talking but us on the recording, but you can leave if you don't like it recorded. It does not record who's in attendance, okay? The presentation materials that we're going to go through today are all out on the wiki, along with a white paper that has been presented that's going to be talked about by Earl. And also we've got today as part of our topic a testimony. This will be a first for the VUG webinar. We've got a testimony, and there's a few charts on that. Those are out on the wiki as well. And so I just want to put that out there. So as you might know, if you're familiar with being on this, we have a Q&A session, a Q&A-like window, and a chat window. If you have questions, please put them in the Q&A window, okay? That's where we're going to be looking at for questions, and then we can see them and answer them, and you'll see the answers as they come up. If you want to chat, you have things to chat about, go ahead, put them in the chat window all you want. That's fine. But if you have questions you want us to look at and answer, please put them in the Q&A window. Now let's get on to our topic. So the topic of the day is how to build really, and I'm kind of going to fudge up here a little bit, but it's really how to build your LPAR based on the workload that's running into it. All right, so kind of exciting. And we've got to present to us today is Earl Jew. Earl's been a speaker. Actually, he did a couple sessions with Tom Prokop earlier on in the year, and he spoke to us many times before. Earl is part of the lab services. He's a tuning guru, knows all about the depths of AIX. He's just super talented, and I'm lucky to know him and actually to have worked with him sometimes in the past. Now, if you've heard Earl talk before, either on one of my webinars here or at one of the IBM conferences, he speaks for TechU as well, you know that it's hard to keep up with him. And it's not because he talks super fast or anything like that, but there is so much information that is flowing that it's just hard to keep up and keep up with it all. So here's some fair warning. Try to get away from your distractions for 90 minutes, focus up, and hang on, because I'm sure that we're going to have quite a ride and learn a bunch here with Earl. With Earl, we've got Tom Prokop. He's kind of sitting back. He might be answering some questions that are typed in and probably chime in. And then we've got a surprise speaker that's going to give some testimony here. And I'm just going to wait until we get there and let Earl introduce him when we get to that. So with all of that, Earl, I'll give it over to you.
Oh, thank you for that introduction. That was amazing. At least I don't know. Strategy for specifying Power 9 AIX LPAR implementations. This is specifically about Power 9, but I got a few things to say about Power 10, okay? This is the 2020 curriculum, not the TechU 2021 curriculum. And back in October of 2020, all 6 of these sessions were a formal learning path leading to a badge. Oh my gosh, I didn't write it for that, but they did that. And of course, I have additional additions, amendments. The January-February VUG had these 3 sessions, and I lengthened them because I have 90 minutes on the VUG versus what I present at TechU. So these 3 versions are enhanced a little bit longer, a little bit more involved. This mapping one I didn't actually present live because it was just too deep. What we're doing today, though, is a strategy for specifying implementations. That's what we're doing today. That's the abstract. You can read the abstract, and this is how to reach me down here. This abstract is just down to this. First, understand the workload, its priorities, its character, and then build the LPAR, the most appropriate LPAR. That's what this is about, a strategy. Not many tactics in this. This is an overall consideration of concepts. Tactics are found throughout the rest of my curriculum, but strategies are not about tactics. It's about what an architect ought to be thinking about. What do we do in the Powerverse? We generally build a generic shared processor LPAR, what I call a best practices default LPAR, and then we put the workload on it, and that works most of the time. Not that it doesn't work. I say that we ought to be doing it the other way around. I say we ought to first understand the character priorities of workload and then build the right LPAR to put on it. You go figure out which way you think works better. For most little workloads, dropping a workload on a generic best practices LPAR works just fine. But our workloads are generally getting bigger with more data. So I say, learn what your workload is first, then build the LPAR match. That's where we're going. I'm going to give you an overview. The three things I'm talking about are primary demand, responsiveness, throughput, and continuity. Continuity is my word. It's not published anywhere. I'm going to define it. Responsiveness for OLTP, throughput for batch, and then priority workloads. There's low priority workloads, there's high priority workloads, there's production workloads, and there's Black Friday priority. That regards continuity. So we're going to talk about these three aspects. The key point is that these three aspects map to continuums. So here we talk about continuity with variable priority, and the three continuums regard the degree of priority for your workload, whether your workload's nature of priority is responsiveness or throughput, and of course, depending on the nature of priority, you measure the performance of priority differently, right? You measure responsiveness differently from throughput. Degree, nature, performance actually map to continuums. Performance or priority, you judge it by performance or efficiency. That's a spectrum, a continuum. You want high performance, you're not going to get high efficiency. If you want high efficiency, you're not going to get performance, a mutually exclusive continuum. The same thing with responsive. If you want high responsiveness, you're not going to get high throughput. You want high throughput, this end is the highest throughput. You're not going to get the best responses. And continuity, discontinuity is how you build the LPAR. These two determine how you build the LPAR. And which way you build the LPAR depends on its degree of priority for whatever criteria is your primary demand. Performance or priority is based on performance efficiency, and this is how we judge how much entitlement to give. The ILCS all value regards entitlement. Now, I'm hoping this stuff will eventually filter out to LPAR to RRD and MON, my favorite tool. That number there, though, is not emphasized, though collected. This here is having to do with entitlement. If you've got 4 digits in the all line of ILCS, that maps to a knowable performance compromise, no matter how big or no matter how small is your workload or LPAR. These numbers hold. And how do you adjust ILCS, even though you may not understand my writing here? It's about if you have too high of an ILCS, you add entitlement. That's how you control it. This here is 5.3 entitlement, but the LPAR is trying to use 12.47 processors consumed. Yeah, if you want to reduce this number, increase entitlement. course, that's not noted anywhere because ILCS, VLCS, and LCS are not well defined. Nobody's know what it is. I wrote about it. Next is the nature of priority. You have this, you're going to find it on the VUG, best practices guide written by the developers, performance people. This slide is not mine. Oh, okay. You see some edits here because I had to make it a little clear. So there's edits here. You won't find these edits in this actual PDF you'll find on the VUG. Anyways, this concept of responses throughput is from this document. Where I say responsiveness, what's it say down here? Best response time, poorest throughput per processor consumed. That's part of the definition of throughput. How much productivity is there per processor consumed? A key point in definition. Across over here is what I call absolute throughput, where you have the worst response times, but the best throughput per processor consumed. Part of the problem with an understanding of throughput is that there is no definitive tactical definition of what throughput means. Now, I'm not going to get into it deeply here, but in my 2022 curriculum for TechU, if my sessions are accepted, is going to be addressing that. And I actually start writing for October 2022 in January. It takes me 9-10 months to write everything that I've been written. So for the last 2-3 years, it literally takes me 9 months to write these sessions. Degree of priority. Depending on your degree of priority, Black Friday, production, non-production, it determines how you build on this spectrum of continuity to discontinuity. Joe, Dave, Tom, if I'm speaking too fast or I missed something, you just jump in here and tell me to clear it up. All right. The control for how you deal with continuity, discontinuity is based on how you choose to build this LPAR. You've probably seen this slide before. We're going to get deeply into this slide later on down, so you don't have to memorize anything. But way up here, perfect continuity is a dedicated CPU LPAR, and perfect discontinuity is way down here with low entitlement, with AME enabled, and mode 8 on SMT 8 kind of thing. So this is how you control. This is where we're specifying how to build the LPAR. Right? That is a total overview. That's an overview of the whole session. Primary demand. This guy, Jamie Lannister. For those of you who have never met me, I'd like for you to believe that I look like him. For those of you who have met me, you know that this is hopefully the only lie I give you. Session. Whenever I watch Game of Thrones, I relate to this guy most. Here is the main theme slide. We're going to come back and forth in and out of this main theme slide. So you have a map of where we're going. This is what I mean by primary demand. OLTP workloads generally don't care much about throughput. Its primary demand is responsiveness of transactions. And same with throughput for batch. Batch workloads generally don't care about responsiveness. Continuity, that underlies everything. Let's go through these one at a time. Responsiveness. We're going to detail responsiveness. Responsiveness, primary demand, OLTP. By definition, OLTP workloads are transactional and often interactive, and these workloads care for transactions to complete as quickly as possible. This is a very, let's just say our best practices do not assume this. This is a new and emerging technical problem for me, because most people build best practices LPARs to run these workloads, and responsiveness isn't so good. OLTP workloads generally are cloned processes. That means many processes sharing the same code. That's why I call them clones. Now, this is the assumption underlying OLTP workloads. This is what I'm tuning by. the character of the workload. Clone processes are many processes processing data, different data, in the same fashion. And clone processes for OLTP generally are many of them. They're smaller processes. They're generally single-threaded. They may not live very long, and they're intensively tall. Intensively tall means you got a process sitting there. It exists. It doesn't hardly ever run, but when it does run, it runs really hard for 1, 2, 3 seconds. That's what I mean by intensively tall. This is the general profile of what I'm tuning by, because I got to tell you, what does the workload look like so we can tune to it accordingly. Typically, clone processes are what's executing transactions on the run queue. We need to understand that a run queue of transactions in an OLTP environment is crazy, chaotic, volatile, coincident, and episodically manic, meaning when it goes crazy, it probably does that for a duration. There's a distinction between the processes that exist, whether or not they run, and then, of course, what's spawning those processes to run. That's the transactions on the run queue. Most important for responsiveness, you have to have core capacity. That means entitlement. For the entire volatility of the range of your run queue, you got to have enough core capacity to manage the mostest that run queue ever reaches to. Because if you're trying to run process the transactions of a run queue that overwhelms your core capacity and your virtual CPU count, which is really rare, but you're not going to run as fast. So you need to have enough core capacity to cover the entire range of expectation of workload. All right, so that's the whole slide. Every subsection I end with a summary slide before we go to the next section. This is responsiveness, next session. These are the 3 points that we're going to tune by. Transactions as quickly as possible and the character of those processes. Scooch it up. All right. I'm introducing a concept of optimal responsiveness. My view is there are missing perspectives underlying optimal responsiveness because we are all in the long habit of tuning by SMT2, starting with Power 5. Obviously, the reality is today, Power 9, Power 10, we're SMT8, but we're all still living in the inertia of Power 5's SMT2. That's a problem. We are not adapting our habits to SMT8. We know it there, not adapting to it. So that's what this is about. First realization of a missing perspective is processing is fragmented duration. The actual processing of threads stops and goes and stops and goes and stops and goes based on SMT, based on how amount of entitlement you have, as well as CPU virtualization by Power VM. That means virtual CPU migrations, thread migrations, the availability of L3 cache and where that is, all these things causes processing to stop and go and stop and go. If you don't know the duration of processing is stop and go and stop and go, because that's what AIX is showing you, you can't tune by it. Gosh, that was a whole lot said fast. Joe, am I comprehensible or am I just shooting along? All right.
No, you're doing good. You're doing good, Earl.
Oh, yeah, you guys keeping up? Because, you know, I wrote this. I know it. Danny. Mr. Singley, my best to your family. Running 2 TIDs per virtual CPU longer within fewer 10-millisecond intervals is optimal responsiveness. That is one yo of a statement, guys. And I was about to leave it like that because I thought it was intuitively obvious, but no. I need to, thank you, Darren, I need to display this. Let's get into what this detail. Running with 2 TIDs per virtual CPU. My shorthand one TID left and one TID right on a Power 9 vCPU core. What's this syntax vCPU core? That's my shorthand for when a virtual CPU is on a core. When a virtual CPU is not served by a core, nothing can happen. When a virtual CPU is not served by a core, it can only wait for a core. So this syntax means when a virtual CPU is actually served by a core, there's one thread left and one thread right. Huh? Well, let me tell you what that means. This is Power 9 SMT8 on our hypervisor. We've got one SMT4 core left and one SMT4 core right, and we fused the two to make an SMT8 core. This is similar on Power 10, is similar on Power 7, and similar on Power 8. We've lived this way a long time. Not exactly similar, but similar. When I say one TID left, I'm talking about one thread running on the left side where 4 slices, 2 slices per super slice, and another super slice focus the entire SMT4 core on the execution of a single thread. This is a big deal. The whole essence of this SMT4 core is focused on executing one thread. That's what I mean by one thread left, and of course, one thread right. This really means the SMT2 mode of an SMT8 core. This SMT2 might be hard SMT2, SMT-CTL-T-2, or it may be the real-time dynamic mode of the SMT8 core in SMT2 mode. The reality is our cores can change SMT mode. X might be 8, the core might be in 2, given the workload on the core. That's why I come out to say this is running 2 TIDs per virtual CPU means one left, one right on Power 9 and Power 10 and Power 7 and Power 8. That has some Power 6, I don't know. A little different piece. Right? That's what I mean by running 2 TIDs per virtual CPU. Right? That's what that means. My shorthand. You won't find that shorthand anywhere. Running longer within fewer 10-millisecond intervals. We all want our threads to run fast. It's great when threads run fast. Where I'm going is, how about running threads longer within a given interval and running fast? That's the missing perspective. If you don't know processing is fragmented in duration, you have no sense that you can run longer in fewer intervals. That's where this is going. Our VM manages a virtual CPU while served by a core. Remember, that's virtual CPU on a core. That's the syntax notation. In 10-millisecond timing intervals, down here is my highly sophisticated graphics of 16 pound signs to represent 10-millisecond interval. Yeah, my graphics are not terribly inventive. I get it. This here shows a single virtual CPU core over time, 6 10-millisecond intervals. So that's a progression across time. And across all 6 of them, we have 16 milliseconds of virtual time base in 60 milliseconds. This VTB virtual time base, if you want to check it out, is mpstat-v space 1, and you'll see a column on milliseconds virtual time base are right. I'm not making this up. X of AIX. And this is a progression. Same virtual CPU across. This next one is a big leap. That's 1 TID on a virtual CPU core at SMT8. This TID ran 2 pound signs, 2 pound signs, 2 pound signs, 2. That's 12 pound signs, or 1/8 of a core at SMT8, across 60 milliseconds. That means in order to get 12 pound signs of attention, it took 60 milliseconds. Granted, you may run fast in every one of these, not running very long in any one interval. That issue of fragmentation I'm bringing up. You've always known it's there. This here is fully blown. That's 8 TIDs at SMT8. This is a whole lot of work going on, but not very long across many intervals. This here is actually the essential essence of absolute throughput. Meaning, you put 8 threads on a core, there's no part of that core that isn't busy. It's always busy. The good thing about putting so many threads on a core, or virtual CPU, is that busy virtual CPUs don't fold down and they don't seed. Concepts of Power VM, barely visible in AIX, my past presentations. Oh, by the way, for any of you out there, you don't have my TechU content for any year, just send me a note and I'll send it at you. I got a real repository library and IBM box of more stuff you can shake a stick at. All right, that's 8. That's 4 TIDs at SMT4. That might be hard 4, SMT Max 4. It might be dynamic soft SMT4, but that's what 4 TIDs look like. Notice that this doesn't run very long and that runs twice as long at SMT4. That's a longer duration per interval. And this is where I'm going here. Oh. Excuse me, that's the old man take pills alarm. All right. 2 TIDs at SMT2. Notice how you're running longer in every interval. This is 2 threads across 6 intervals. That's a whole lot of time per thread, right? And the point what I'm making is this. How about running longer in fewer intervals? This blue thread took 3 intervals to complete for 16 pound signs. And this red here, orange, took 3 intervals overall for 16 pound signs. Okay? That means your transactions complete in fewer overall 10 millisecond intervals. That is the point of what I will define as optimal responsiveness. This is what I wrote. Okay? I wrote this in the beginning, which is down here. And this is where I've just illustrated to you how processing is fragmented in duration by SMT entitlement and CPU virtualization. This is a missing perspective. This perspective here of 2 TIDs per virtual CPU running longer and fewer is the bestest for running that kind of workload. Meaning, when you have this kind of workload, you want this kind of LPAR, which is what I started with, right? When you understand what the workload is, you attend that workload with the recognition of fragmentation of duration. This is, of course, something that AIX show you a whole lot about. But I believe you hear it. Okay, so that's my first 2 missing perspectives and realizations. Here's another one. It's the other end. Executing 8 TIDs per virtual CPU in each and every 10 millisecond interval is absolute throughput. Now, I don't encourage you to reach as far as absolute throughput, but you need to understand what is the MOSIS in throughput. So, how to monitor it, how to recognize it. So I'm showing you the other end. This is a big, both statements are huge. So let's go detail this. You've seen this already. That's executing 8 TIDs per virtual at SMT8. And what do I define that as? I call that absolute throughput. That means the most. You're running like this all the time. There's no part of any core with nothing to do. And throughput is a statement. Throughput is defined as processing productivity per processor consumed value. And the problem we're having, you guys don't know it, is that you have high processor consumed values producing less than what that processor consumed CPU time can produce. We are, by lack of practices, running with low throughput for the lack of definition of what throughput means. This is the most absolute throughput. Every interval running at SMT8. Throughput is not responsiveness. Throughput is the productivity per processor consumed. Get to that. This is what SMT8 looks like. This is 2 threads on 1 super slice. That's why they don't run very long. This is 2 threads per super slice, 2 threads per super slice. This is why all those cores completely used up, because you're putting 8 threads each. This is what I mean by absolute throughput. When you have 8 threads across every virtual CPU, before you fold up the next core and put 8 threads down. This is the worst response time, best throughput. Absolute throughput is you run every core like this ever and always. Responsiveness. That's the other end. This is default. This is default, Power 9. Best response time, poorest throughput. That means we spread all of 1 thread across all of our virtual CPUs, and they all run real fast, but your processor consume number is very high for the poorest amount of productivity per processor value. And the other extreme is here, of course. You only fold up 1, but you use it all up. Those are the 2 extremes. You have this paper. Okay? It's out there now. This is what I call optimal responsiveness. This is absolute responsiveness based on SMT1. The statement to follow. SMT1 on Power 9 powers down the right core, or the left core, and runs that 1 thread on the core that didn't power down. That's why the throughput is so low. Why I call it absolute responsiveness, which is default. Optimal responsiveness does away with that powering down 1 core of 2 SMT4 cores. This is why I call this optimal responsiveness. There's a call for this, and there's a call for that. I just want to make a distinction between absolute and optimal, because optimal uses both SMT4 cores always. This here is what I mean and why I say optimal responsiveness is running 2 TIDs per virtual CPU longer in fewer intervals, 1 left, 1 right. Don't power this one down and run 1 thread here, which is default on Power 9. This is 8 threads per virtual CPU. This is my definition of absolute throughput. Boy, you get a lot of throughput. Responsiveness doesn't work so well. Each thread doesn't run very long, but there's no part of the core in the PC value that is unproductive. I state, we all have high PC values with low productivity. That's poor throughput. But nobody talks about throughput. I will in 2022. Come to the show in 2022. So here we have it. Fast realization. Optimal responsive absolute throughput are endpoints on a continuum. I established what they look like. They're endpoints on a continuum, and those endpoints on a continuum is something we don't understand. Our understanding of performance, whether it's throughput, whether it's responsive, is a confusion of the traits between one end, optimal response, and the other end, absolute throughput. Without a sense of this continuum, how the heck you guys tune? I don't know. I've been tuning by this for a long time. I'm finally putting it in colorful PowerPoints. That's the whole slide. On to the next. This is throughput. I think this character is cool. Throughput is for batch workloads. Primary demand. How productive is every processor consumed? Okay? Batch workloads, what is the character that I assume when I'm trying to do this kind of tuning? Well, batch workloads, long duration, non-interactive, you repeat them all the time, you move a lot of data, and they're projects versus transactions. Next, other assumption, and this is relatively true everywhere, your batch workloads are fewer, larger, long-lived, multi-threaded processes that are executing multiple shared images of code. What I'm talking about is a variety of clones that are fewer, larger, long-lived, and multi-threaded. This is the base assumption of most batch workloads. This is what I'm tuning to. The character of the workload determines how you build that LPAR to attend that workload. I have to give you what my starting assumptions are of that workload. Batch workloads, performance is measured end-to-end execution duration. Okay. And the great thing is batch workloads are very easy to tune by me. From my sense of it, our best practices are assuming a batch workload. And these batch workloads, man, they have a very broad forgiving range to be feasibly executed by almost any implementation, allocation, and infrastructure. In grave contrast, OLTP workloads. This is the simplest, easiest. Batch workloads don't require a reserve of core capacity for volatility of the run queue. Since you run batch workloads so often, repeatedly, you know that range of the run queue. It's not a volatile run queue. It's about the same between most runs. And batch workloads don't care about responsiveness. Of course, it's a grave contrast to all TP workloads. So these are starting assumptions. But the key one is down here. Throughput is a measure of productivity per processor consumed at your choice of SMT, hard SMT. I should have put the word hard there. Summary slide. This is the whole section, and on to the next. Oh, look, this is what we care about. Excuse me. These are the 3 points we care about. I'm going to scooch it up, and talk about the first. If your end-to-end executions meet or beat your SLA expectations, wonderful. But sorry, there's still more to be considered. Meaning, yeah, you're meeting your SLAs, but there's yet more to consider. What more to consider is under this heading. In stark contrast to the exceptions of OLTP workloads and databases serving response-sensitive batch workloads. This is a hybrid workload. You got a database that's serving response-sensitive batch workloads. This is an exception as well as OLTP. With the exception of those two, most batch workloads are housed on outlandishly over-provisioned shared processor LPARs. Yeah, that's you guys out there in the Powerverse. All of you have too many virtual CPUs, especially for hard SMT8. Chances are your count of virtual CPUs is sized for Power 5, Power 6 at SMT2. But we're SMT8 now. You see, the higher is your SMT, the fewer virtual CPUs you need. But nobody reduces their virtual CPU count as they progress from SMT2 to 4 to 8. That is a problem. The problem is this with this entrenched trend, which is so darn stubborn, is that it defeats the economic advantages of deploying our late technology at hard 8. Okay? This is a problem. You guys buy this good stuff, and you have too many virtual CPUs. For the workload. You know, you're all running SMT1 with a little SMT2 and some SMT4 for kernel. I mean, you guys have trouble seeing that, engage me. I do those kinds of engagements. That's what I do. Engage me, and there's various methods to fund my attention. When you learn the character of your workload at this level, you will see things you never imagined, and now you begin to tune it more creatively. David is a wonderful expectation of that, all right? Example of that, okay? What you're supposed to do with all batch workloads running within the SLAs is you should routinely test with fewer virtual CPUs until reaching the edge of your SLAs to reduce the cost of software CPU licenses. This is the main economic advantage of our power technology. You need fewer licenses. That's where your savings are. What do I find? I find it routinely. People are buying 20 licenses and only using 5. Did anybody realize that paying for 20 licenses is more expensive than paying for 5? I don't, maybe you guys can explain it to me. Why do you guys buying 20 and only using 5 routinely? That's a problem. That's the whole slide. On to the next. Throughput. A measure of processing productivity. My view. Our sense of throughput is utterly undefined, undocumented, unknown. Yet it's desired. What? We all want high throughput, but it's undefined, undocumented, unknown. You know, there's a problem there. We want something, but we don't know what it is. Tom, Joe, tell me here, is that statement true to you? Did IBM ever teach us the meaning of throughput?
Only you, Earl.
Only me again, huh?
Yeah.
How come it's only me, guys? How come it's only me? This shouldn't be that way. Anyways, first realization. Absolute throughput cannot be observed when you don't know what it is. No reference, no definition, no means of recognition. This is a problem. If you don't know your destination, how do you know how far you are away from that destination? That's the first realization. Next realization, some definition for this priority must be established. I'm not going to do it here. You don't know what it is, how are you going to monitor for it? Okay? Next is this, last realization. You know optimal responsiveness, you know absolute throughput a little bit. And the realization is they're endpoints of a spectrum, and our understanding of this continuum is not very good. Because performance is either responsiveness or throughput. One or the other. So what do I get? I get customers saying, my performance isn't going very well. And I look at the LPAR and I'm like, wait a second. What do you mean by performance? Well, they actually meant response time, and I assume throughput. So that's where I have to evolve to these ideas. That's everything there. On to continuity. This is continuity. Hello, Danny. Continuity. Primary demand of priority workloads. Means your subjective priority workload is a trait of continuity. Continuity, switching it up. What is continuity? Well, it's not a published word anywhere. It's just mine. It's my word for everything AIX simply assumes is always continuously available when the truth is it isn't. AIX, properly designed, simply believes that this concept is always continuously available. Continuity is mostly not a concept consideration concern of AIX because AIX simply assumes and forgets. Proper. It just assumes and forgets, which is, the realm of virtualization. What is it assuming and forgetting? Well, continuity is about the immediately available continuous readiness of SMT entitlement Power VM to attend a workload. When a workload comes along and is immediately available and continuously ready to run that workload, that's called continuity. But AIX always thinks it's always available. That's what you see, by the way, when you're watching it. This concept of continuity is always assumed in AIX, which is why it's so darn hard to teach and to see. The converse is the other, the unavailable delayed readiness of SMT entitlement Power VM to attend that workload. There is a delay when it's not ready. That delay is summed up in the word discontinuity. So when it's always available, you have continuous readiness. When it's not available, you've got discontinuity. It ain't ready to run. You got to set it up to run. Now, this is simplified subjective language here for strategic understanding. Tactically, continuity versus discontinuity has always been there. I'm just giving it fancy poetic words. Continuity is simply keeping a virtual CPU where it wants to stay, where the cache is hottest and local, where prefetch is aimed, where it's not preemptively disrupted by a lack of entitlement with ILCS, and you're not migrating your virtual CPUs, and you're not folding them down. What does this describe? Perfect continuity is a dedicated CPU LPAR. Once you boot a shared process LPAR, you have introduced converse. A shared processor LPAR has progressive degrees of discontinuity, that which is not met with continuity in each of the above. I'm not saying shared processor LPARs are bad. They're not. They're actually wonderful. You just need to understand how to use them better. The concept of continuity discontinuity is that shared processor LPARs are progressively more discontinuous if you starve them, if they're too small, if they're too wide, if the affinity is bad. So that's why I have to come up with this concept. We have continuity good versus discontinuity bad. The readiness to accept workload. If a virtual CPU is not on a core, it's going to be unavailable and delayed readiness. When a virtual CPU is folded down and you throw workload at it, it's got to spin up that virtual CPU, schedule it to a core, then throw workload at it. That's what I mean by unavailable delayed readiness. Well, if your virtual CPUs never fold down, you never have to worry about folding them up. Okay? If your virtual CPUs never migrate, the cache is always hottest. Prefetch is always aimed right at it. Well, virtual CPUs migrate between cores in shared processor LPARs. This is part of what I mean by execution is fragmented in duration at multiple layers outside the site of AIX. Where I step in. And how you control continuity, discontinuity? It's how you choose to build it. AME active or not, your VPM throughput mode, how much entitlement you give per virtual CPU, if you boot dedicated, donating, where you turn on, off, and pull. These are all concepts where we can get into specifying LPAR. So that's the whole summary slide. On to the next, a synthesis, how to see it, how to synthesize all the concepts in the what to know that I've given you. It's pretty easy. It's nasty. Continuity by priority of workloads. All priority workloads crave continuity, but not all priorities, the lower priorities, they don't deserve that continuity. You can build them to run slower. What I'm saying is the degree of priority of the workload determines the degree of continuity to be implemented. If you have an extreme high priority, which I call Black Friday priority, you want as highest degree of continuity to be implemented. So your degree of priority, that's your subjective sense. Nature of priority. Are you responsiveness priority or throughput priority? Which primary demand is it? Well, some of you may have workloads where it's both. Okay, if it's both, you better decide upon one. One is usually more important than the other. I don't know which it is for everybody. Sometimes the night batch workload is more important than the OLTP. Sometimes the other way around. So you're going to have to decide what is your sense of nature of priority. Because depending on that nature of priority, you measure the performance of priority differently. Right? Performance of responsiveness is different from performance of throughput. That's the key point. All three of these, degree, nature, performance of priority, maps to three continuums. You've seen this already. Those are the three continuums: performance efficiency, about entitlement, the nature of the workload, and of course how you build it. The performance efficiency, responsive, throughput continuums determines how you build the LPAR. So they map like that. Next, the matrix of three continuums. This is the main theme slide that we're going to come in and out of. We know that they map on those three continuums. I'm going to restack them for definition. Performance efficiency. I actually have numbers that define executing with enough entitlement to run as quickly as needed. You see that arrow far left? That's maximum performance. In contrast, is efficiency. All the way right is the least entitlement to achieve tolerable performance. I have numbers to define tolerable performance. So you're either max performance or you're max efficiency. And the factors are common to all of our understanding. The factors are how much entitlement to how many virtual CPUs you build. This is in your realm of LPAR profile parameters, okay? You guys do this already. Next one, responsiveness throughput. Responsiveness, completing transactions as fast as possible. All right, maximum responsiveness. The other end, of course, is throughput. Maximum processing productivity by your PC number at your choice of SMT. That's maximum throughput. This maximum throughput far right means maximum throughput. As this arrow goes to the left, you get less throughput, but more responsiveness. Okay? And what are the factors here? This is where I have something value add. Your factors is your choice of max SMT, counter virtual CPUs, and the VPM throughput mode. That blue bold and that blue 8 bold is default power 9. We are default SMT8 mode 0. This red here is default power 10. Default power 10 is red, mode 2. Now, those of you who have followed me for a couple of weeks or years, I've been screaming about mode 2 default since power 7. In power 10, they done did it. They didn't do it because of me, believe me, all right? But now mode 2 is finally coming in power 10, meaning we've got better numbers here, all right? Anyways, that's what this, and going on down here, the continuity, discontinuity, defined continuity, I tell you, discontinuity is a progressive degree of what it's not met. And the factors here is how you build the LPAR by your choice of continuity, discontinuity. What? You build the LPAR by your choice of this. And that falls to this. It's your choice, how you build it. All right. That's the summary describing each of three continuums. Workload profiles. Now, these profiles are generic. There are probably many more. Three continuums. You know them. I'm going to start off with what we all know how to do so well. It's the best practices, default AIX shared processor LPAR. The next category is where I step in with batch workloads, low priority for completion. That means you don't care how long it takes. That's non-prod stuff. Batch workloads with high priority for completion. When I say high priority for completion, I'm talking about what I consider common production. And then Black Friday is extreme priority for completion because batch workloads need to complete in shorter durations, right? I mean, that's. And next, of course, is shared processor LPARs for OLTP workloads, which is different from batch. OLTP workloads care about responsiveness. Well, what do I have? Non-production responsiveness. I can't think of a non-production responsiveness OLTP workload unless you're doing development on OLTP just for logic checking or something, right? But that's, I got a category for it. Common production responsiveness and Black Friday. Those are the 7 categories we're going to map how we should build them. Implementations. This is really it. I'll leave time for Dave. All right. Best practices LPAR. How do we build it? We build it like this. Remember the 3 criteria here? You have a broad range of performance and efficiency, not max performance, but by your choice of entitlement. That orange means you accept the default of SMT8 mode 0 or mode 2 on Power 10, and you accept the default of continuity discontinuity. That means these two have no factors. You only choose entitlement out of virtual CPUs in the default best practices LPAR. Okay? You control the entitlement here. What is your ILCS? Too high, too low? You adjust it. And here, 1 to 2 digits, perfect. That's hypervisor only. 3 digits sustained is warning. 3 digits sporadic, acceptable. 4, 5, I've never seen 6 digits ILCS. Even if you don't understand what it means, you're going to run that syntax and monitor it. And you adjust your entitlement as you care. Okay, that's the best practices LPAR. It defaults to what I call absolute responsiveness. We fold them all up and put 1 thread on all of them. That runs fast. That PC number is huge. Not much productivity. Okay? That is the default of Power 9. Oh, what's that? That's absolute responsiveness on Power 10. This doesn't exist on Power 10. You can turn it to it if you want, which I did, but by default, we're this, where you should stay. Absolute responsiveness is defined differently on Power 10. We tune to the technology as the technology advances. So when you build the best practices LPAR, it's SMT8 at mode 0. You choose the counter virtual CPUs. You choose entitlement. Voila, this is simple and done is what you've been doing. Okay, that's good. Let's go on to the next. We're going to go through low, high, and Black Friday for batch workloads, okay? Comparatively, batch workloads, end-to-end duration, I defined absolute throughput, 8 threads per virtual CPU ever and always is absolute throughput. I don't want you to run at absolute throughput, guys. It's just an ideal, a mind, a concept, and understanding processing productivity. That's what we care about. Okay, so here, low priority of completion is the mostest for efficiency, the highest for throughput by the definition of throughput, and the mostest for discontinuity because you don't care how long it takes to run. Batch workloads, if you don't care how long they run, you run them most discontinuous. This high throughput here shows responsiveness is yellowed out. Why? Batch workloads have no concern for responsiveness in general. That's why I yellowed it out. As you go to common production, you see the throughput actually drops lower, but the performance picks up. As you go to Black Friday, you see you have the highest performance, the lower throughput, lower standard throughput, but absolute continuity. That's for Black Friday. So that's how we should visualize the concept of throughput by priority. So let's go to building each of these. Shared processor, low priority. When you build a low priority batch workload for completion here, you want the highest efficiency, highest throughput. You don't care about discontinuity. That means running with high preemptive disruption with 4 digits ILCS. All right, let's go through these here. When I talk about tolerable performance, I'm talking about 4 digits. Pink, background is pink. Tolerable performance design is 4 digits per second. That's why that number 1's there. Pink background means this pink background, 4 digits, that number. You can see that that's notable performance compromise. I call notable performance compromise tolerable performance because that's how most of you are running right now on a best practices LPAR. You're running at about 4 digits all the time, and you tolerate it. Fine, okay, I'll call it tolerable. I'm not mad at you guys, by the way. I'm happy you're here listening. You adjust your entitlement as you need. This is where it's very different. That highlight yellow means it breaks from default. For low priority batch workload, you want SMT8 mode 8. The highest possible throughput, which is what this says. Absolute throughput, mode 8. Okay? So for a low priority batch, yeah, this will get you the most. By the definition of throughput, how much it produces for how little PC. This is what SMT8 looks like. You've seen this before. I have said 8 threads, every interval, absolute throughput. This is what SMT8 looks like. Okay, absolute throughput looks like this. Every super slice gets 3 threads. The contrast to that is, there it is, SMT8, mode 8, low priority batch. We go on to common production batch workloads. This is what I propose that most of your workloads, batch should run at. Common production. We want to have enough entitlement to run at 3 digits or less of ILCS, which is a blue background, this blue right here. 3 digits sustained is warning. Now comes the break from default. Throughput here is less throughput, better performance. And I suggest max hard 4 at mode 2. I think Dave would agree. This is pretty cool. Okay? This is what it looks like, which is default on power 10, by the way, okay? And so you put 2 threads per virtual before you fold up the next. SMT4 is available, but you basically dispatch actively at SMT2, and when that workload grows, you go to SMT4. Okay? So that's what I mean by max SMT4 at mode 2. This is 2 threads at SMT2, right? You're running your batch workloads through longer threads, and this is SMT4. So for optimal throughput, it'd be SMT2 and SMT4 because you want your production LPAR threads to run at the least 25% of a core. That's why it's between here and here. This is SMT4 on an SMT8 core. You've got 2 threads across 2 super slices, left and right. This is what I call optimal throughput, not absolute throughput. Executing 2 to 4 threads per virtual CPU in most of every interval is optimal throughput, not absolute throughput. It is a compromise. Between the duration execution of a thread for production versus absolute throughput, 8 threads always. So what do I suggest? My favorite mode, hard 4, mode 2. Again, for the count of virtual CPU's entitlement. Batch workloads, Black Friday. Built a little differently. This is dedicated donating. And we enable virtual CPU folding. This is twisted sister weird. I'm the only one who ever talks about this. When you boot a dedicated or dedicated donating LPAR, virtual CPU folding is disabled. I say for a batch workload or Black Friday, you should re-enable folding. And here's the rationale why. Batch workloads in general are either running or they're not running. When they're not running, fold down all those virtual CPUs, keep them down, and donate that capacity to the shared pool. When that Black Friday batch workload kicks in, though, all your virtual CPUs fold up and you use them like crazy. Because batch workloads are either running or they're not. When they're running, you want your dedicated resources there, but when it's not running, hey, fold the virtual CPUs down and donate that to all of the shared processor LPAR. Okay? So this is the lowest throughput per processor consumed. Remember, processing productivity is how much production there is per PC value. It's a very high PC value when active. You're not much production, but dang it, it runs max performance and max continuity. You build it, simple. Boot dedicated domain, enable folding, voila, you're done. You don't do this for OLTP. Dave did do this for OLTP, but it's not on my advice. It does work, but not me going to tell you that, all right? Okay. Now on to OLTP workloads as a category. What do we care about? We understand that OLTP workloads are of this character, and we want to run optimal responses at 2 per virtual for longer within fewer. This is non-production responsiveness. Less efficient, more responsive, default. Okay? On to production responsiveness. High performance, more responsive, greater continuity, and the ultimate Black Friday OLTP LPAR. Best performance, best responses, best continuity. So you can see where that progression is for OLTP. Let's build out our non-production responses OLTP. What do I say? Give enough entitlement for 4. High preemptive disruption, non-production now. And then we go on to this, right? This is where you end up in pink, about 4 entitlement. And again, SMT4 at mode 2. Looks like this. You see that there's no SMTA threads here. This is pretty good mode, by the way. And that's how we build it. SMT4, non-production. Going into common production OLTP, how most of your OLTP works ought to be built. Sufficient entitlement for low ILCS, you have it in the blue zone, and hard to mode 0. Hard to mode 0, common production OLTP. No concern. This here is absolute responsiveness, the default of Power 9. You can do this on Power 10, but I hope you won't. I don't know the mapping on Power 10. Has not been published. Mapping it. Don't do it. Can, but it's default this, right? So this here is absolute responsiveness on Power 9. Which your SMT2. Hard to mode 0. Pretty simple to build. You're going to need more virtual CPUs with higher entitlement, but you're going to run those transactions fast. Because every thread is running on half a core. Every thread running on half a core means you complete in fewer intervals. Black Friday production. These are the big OLTP retail LPARs I've been tuning, and once I tuned them, it must have been 3-4 years ago, they don't interrupt my Thanksgiving anymore because Black Friday LPARs are all built like this. This is pretty easy. It's hard to, with no setting for VPM throughput mode because you booted dedicated. This is real easy. Absolute perfect continuity ever and always. This is what Power 4 was like always. Except it was 1 in Power 4. So you just put dedicated and be done. None of this stuff. That ends the presentation. And Dave, please be my testimony. I'm going to stop sharing and throw it to Dave. And Tom, none of you guys interrupted me, Tom, but I'm going to stop sharing here. And
thanks, Earl. All right.
So, Dave, I'm going to make you a presenter here. Okay.
Okay.
And why don't you tell us, I don't know, you can do a little introduction about yourself and you know, what you were doing.
Sure. Okay. My name is Dave. I was an IBMer for about 40 years until they kicked me to the curb and made me work for Kyndryl. So I met Earl about 3 years ago, I think in New Orleans. And when he made his presentations, it kind of opened my eyes. And you know, since my client is essentially a power shop, we were a power 8 shop at the time, and we were starting to dabble in power 9. That's it was my team's responsibility to manage, you know, performance and capacity planning and stability for the power platforms. So that's kind of where I came from. And let me go ahead and start sharing here. Let's see. All right. And now I'm going to start the. Okay. All right. So what I'm going to share with you is an activity that we've performed. My team has performed over the past year and a half.
So we can't see the charts or anything yet, David.
You can't.
No,
Really?
I see a pretty colored screen, purples and blues, and white. And,
Really?
yeah.
Interesting.
So I don't know. Depending on how you shared, you either don't have it as your primary, or else you didn't share the whole screen, or something like that.
My screen. Let me see if. Let me try this again.
Same thing.
Okay, all you're seeing is my. Okay, so let me try this again. Okay, let me try one more time. Share. Huh.
Well, it's a different size now, but it's the same.
Well, yeah, that's because I shared. I've got a dual monitor setup, and I shared.
Are you sharing the whole monitor? You share the whole screen?
I am well, I'm doing a share my screen, and try this again. No,
Nope.
it's not working for me.
Want me to share it?
Yeah, why don't you go ahead? You know what I want to share, right, Earl? That
okay, Earl, I'm making you the presenter again.
Okay.
So while Earl's bringing it up, as I said, we were tasked over the past year or two to reduce the license costs of the software that was running on our Power 9s. Okay, and you go ahead and move it to the next slide, Earl. And we wanted to, you know, we were asked to do this without sacrificing end user responsiveness and batch throughput. And I'm only going to talk about a little slice of what we did. Okay, we did a lot more, but this is the, I guess I'll say, the biggest slice. And what we ended up doing was migrating LPARs with high cost software, and that included Message Broker, Transformation Extender, and WAS from our P8 servers, which we had about 20 P824 servers. We migrated them to the P9s. We have 6 P924s. And as we did that, we applied the tuning principles that essentially Earl reviewed here. And the specific application I'm going to talk about is it's a call center application. It during the daytime, it has anywhere from 2,000 to 5,000 users, and what these users are doing is basically pounding on basically on a web browser, and those web requests are going to a number of application servers, and those application servers are either going to a database or processing, basically calling external services or internal services through our local mainframe. So that's what's happening there. And, you know, the day work ends about 5 o'clock, you know, while all the call center guys go home. And then batch processing occurs overnight. It validates, syncs, and makes the data whole by 6 a.m. to be ready for the next day. And our application servers are essentially HTML processors The stack is, WAS with Pega sitting on top of them, and they're in clusters of 3. And our production includes 12 total LPARs, excluding our database LPARs. And based on the observations and the learnings that we got from Earl, we formulated a hypothesis. Okay, so the first thing that I'll say is, when we started moving these things to the P9 and we started playing with the VPM throughput mode, the thing I noticed, or the thing that we noticed, was that as you crank up that VPM throughput mode, what happens is the virtual, the PC value goes down. And that actually intrigued me quite a bit. So I was thinking, okay, so if I can keep that PC value down below my entitlement, what will happen is my ILCSs will not kick in. And if I'm not having ILCSs, what's going to happen is, even though I may be running on lower threads, slower threads, because I'm not being migrated off involuntarily, it may offset. So my theory was that if you run VPM throughput mode 4 to the point where you're running continually below your entitlement, that will cause a reduction in your ILCSs, and as long as you're not over threading, the increased opportunity or increased chances for running on a slower thread gets offset by the fact that you're not swapping around and losing your physical cores every time because you're running lower ILCSs. Okay, so that was my theory, and so when we migrated this, we tested this theory as we went forth. Okay, and so we applied a couple principles. One is we don't allocate excess capacity, which means have as low virtual CPUs as we possibly could while not taxing out our box. Avoid exceeding entitlement. Also avoid overthreading. And then another thing is that we used HTTP response times in our servers to measure our responsiveness. And I'll talk about that in a second here. Another thing is, it's okay, at least from my perspective, if your individual threads take a little bit longer to execute, as long as they don't impact your user response time or your batch throughput time. And we ended up doing an iterative incremental approach. We would migrate an LPAR. We'd tune it with the default settings, basically what Earl said, SMT4 with VPM mode 2. We do observations. We tweak the knobs a little bit. And then we'd repeat until we got to a steady state where we had good response time and we also had good consumption. So Earl, can you go ahead and move on to the next slide?
I wanted to explain bullet number 3, avoid overthreading.
Okay.
Overthreading is the run queue value sustains for more than a minute higher than the count of logical CPUs. That is my formal definition of overthreading, that the run queue sustains at a minute or longer at higher than the count of logical CPUs. Okay, Dave, I wanted to explain that.
Thank you. Yeah, and I was going to share that with, but apparently I can't do that. So this is just a high level view of our topology, and the boxes inside this, the thing inside this red box is our core application servers right there. And what happens is we get OLTP from our call centers. They flow through a load balancer, and this load balancer distributes the work amongst these servers. Okay, these servers have AIX Pega WAS, and what these servers do, they get a request. Depending on the nature of the request, they may do database reads or updates over here. They also might go call services, flow through here, go through our ESB, and make calls outside, or make service calls to our internal database, or our internal mainframe. Okay, and typically what we see on a day when things are running well and we don't have anything we see about 100 milliseconds to 300 milliseconds average response time. Okay, so we know what those are, we measure that. And the thing that we found is even though we start turning VPM throughput mode to 2 to 4, and we start reducing our CPU and we start tightening up our threads, what happens is, just because you have a thread that takes, 2 milliseconds instead of 1 millisecond, we still have our SAN, we still have our databases, and we still have our external services, which may take anywhere from 10 to 100 milliseconds. So even though we're running a little bit slower because of our VPM throughput mode, I guess I'll say that you're only as fast as your slowest component. And our services, our external services, is really our slowest component. So we were able to turn our VPM throughput mode down and not see any degradation in our HTTP response times. So anyway, so go ahead. Can you go ahead and move to the next slide, Earl? So doing that, we ended up hosting, we had 6 824 platforms, and we migrated those 6, we fit them all into 3 924s. Okay, our total WAS license count went from 84 to 42. And 84, if you do the math, 14 times 6 is 84, and 14 times 3 is 42. So that's how, and we had these were 16 CPU CACs, and we allocated two CPUs for our VIO. The other 14 were available. And we ended up saving, in this particular case, about $150K a year. And the other apps that I'm not talking about here, we ended up saving overall $150K plus another $100K, about $250K a year for the client, just because we migrated from the P8s to the P9s. We reduced our, we aggressively lowered our virtual CPU. We also aggressively used VPM throughput mode 2 and 4 for our interactive and our batch applications. And our client is fat, dumb, and happy, and they're saving lots of money. So that's basically it. I wish I could share and show you the actual details, but apparently I can't, because I'm WebEx challenged, at least this version of WebEx challenged.
Well, thank you, Dave. Would you say this corroborates that my concepts and tactics are worthy?
Absolutely, absolutely. What you did was you basically, I'll say, I mean, you encouraged us to be aggressive with SMT and be aggressive with VPM throughput mode and be aggressive with lowering our virtual CPU count. And those 3 things alone is what, I mean, and quite frankly, our P8s were way over provisioned. We had probably 8 and 10 virtual CPUs where 5 and 6 virtual CPUs would do. And it's been a challenge because the client, they're thinking, okay, if you're reducing virtual CPU, you're going to reduce capacity. And what they didn't realize is that, yeah, you need some extra capacity in case you have bursts on your OLTP, but you don't need 100% extra capacity, which is what they had. And once we were able to demonstrate that these things will run in a smaller, tighter footprint, and we're leveraging the lower threads, and the client, not only was it running as fast, it's running far more stably as well, because it's running under its entitlement. The performance is predictable, and we no longer have platform performance issues. That's the other thing, is our platform performance is predictable and understandable. And now when there's a problem, when there's a performance issue, the client looks towards the application and the products first before they go back and they say, is there a problem with the platform? i.e., are we running slow, or we have capacity issues? So the client just assumes that we're good on capacity and performance. So yes, what you've everything that you've just said, Earl, works swimmingly.
Well, thank you.
Yeah.
I mean, I don't know how to do what you do, but this is all that I do. I only do performance. I don't know LVM. I can't build a VIOS. I only do performance.
Mm-hmm.
For the,
Well, that's a big part of it.
What you founded it on then, huh?
I'm sorry, what's that?
Is this what you established mostly? My favorite mode?
Our SMT, yeah, that's our OLTP mode, and that's standard. I mean, that's what we start with. Our batch workloads, we go to VPM mode 4.
Ah,
And
you know,
they
that
work.
the presentation, exactly what I presented.
Yeah. Yeah. And I don't know. Yeah. So the one in the yellow line is our OLTP ones, and our batch LPARs run SMT4 throughput mode 4.
Wow. Tom, you've been amazingly quiet. Nobody has any questions?
Well, Tom's been out there answering a few of them. You know, there was one, David, I don't know. Somebody asked if you account for high availability, like if one of the 924 KEX went down, is that something in your?
Yeah, I was gonna, if I was able to share, I would show you. Yeah, what we do is our 924s have 16 CPUs in them, and we allocate 2 CPUs for VIO, and we try to limit our consumption to 12 CPUs. So that gives us 2 CPUs in reserve in case we lose one of the 3 in our cluster. So we have 3 LPARs per cluster, and we have basically we have a red line at 12 CPUs consumption. And that's typically enough for us to survive a hit. But quite frankly, these P9s don't go down. So we've had them for like 3 years, and the only time we've had an issue with them is we've had a couple of DIMM problems. But other than that, we haven't had any issues. But yeah, we do account for HA, and like I say, the way we do that is we limit our consumption to 12 CPUs per CAC.
Okay. So Earl, we're about at the bottom. Do you have any last words of wisdom before we wrap up here?
Yes, please engage me, guys. Please engage me to learn what you don't know that you don't know, because I got a ton of content, guys, and a whole lot more to say than what I present. Engage me, and you probably don't have to pay for it because we find funding other ways, and I don't have enough engagements. So, anyways, reach to me for anything. Always want to make new friends. I do interact with you guys if you reach to me. Thank you very much for this, Joe.
You bet, Earl. And I'll just say, so I mentioned Earl works for our lab services, which is a, you're probably aware, a group of IBM that you can engage. And as Earl said, there's all kinds of different ways to pay for it. But they are the experts, and Earl is one of the experts. And so if you have something going on and you need some help, this is the place to go. And you can contact Earl directly. If you can't get to him, you don't have his contact info or something, you can't find it, you can always contact me, and I'll put you in touch with the right people to get him involved. And I don't do this just to promote lab services. I brought Earl on because he shares a lot of stuff for no charge for this, and this is good learning opportunities for everyone. But if you want more, you can certainly contact Earl, which I know a lot of people have in the past. So with that, thank you, Earl. This has been great. I know you did a lot of modifications on this, and so I appreciate that. And thank you, David, for a wonderful testimony. Like I said, this is the first time we've done that, and I think it's great. And Tom for answering questions. I appreciate all you guys' help in making this a successful webinar. So with that, I want to just say once again, Merry Christmas, everyone. I hope your 2021 wraps up successfully for you in whichever way, and I wish you all good health for the rest of the year and next year as well. With that, I'll be sending out some stuff. I've lined up webinars already for January and February, and I think I have an idea for March already as well. So I'll be sending out some stuff for that as the next weeks go on. All right, so with that, I think it's a wrap, and see you all next year.
Good.
Thank you.